All right, guys. Today we have the pleasure of having Wang from the Queen Mary University of London with us. He's gonna talk to us about some very interesting work he's been doing. Zhaolin, take it away.
Yeah, okay. First, many thanks for Professor Abu's invitation to give this opportunity to provide this talk here. And in this talk, I will share some of our recent work and thoughts about next generation MIMO, which is a very general talk. And in this talk, I will mainly focus on three promising directions, which is very promising in our minds. Yeah. Uh, yeah, let's start with the first slides, which I have some brief background on the MIMO technique. As MIMO have been developed for many of years and still as the core of the 6G or even the following G developments. And during many years developments, we all know there are two main trends of the MIMO. The first one is that we always try to build a larger and larger MIMO so that we can have, for example, higher degree of freedom or serving many of users than ever before. And the second trend is that we try to use the higher frequency bands to support the MIMO system. For example, in the previous 4G and 5G research, people focus on the higher frequency band like the millimeter wave and the terahertz. Although these kinds of bands are will no longer be used in the 6G, but in 6G we still have a slightly higher band, which is called the upper mid bands, which will have the frequency band from 7 to 24 gigahertz, which is still much higher than the conventional sub 6G frequency bands. And the question is that what will be the next research topic for the next generation MIMO? And in this talk, I will share about three ideas. The first one is called the large aperture arrays, which will facilitate the developments from far field system to the near field system. And the second one is called the ultra dense array. And I will focus on how we can design the MIMO from the discrete one to the continuous one. And the last one is the flexible arrays, and I will talk about a very new research technique or antenna technique, which is called the pinching antenna. Yeah, let's start with the first one, which is the large aperture array. As we mentioned before, we know that the MIMO will be developed with a larger array size and higher frequencies. However, the question is that can we realize 6G by simply doing this? Of course, the answer is no, because we have so many challenges to solve. And one of the important challenge is that we have to consider the so-called near field effects of the antenna array when we increase the size or the frequency. We can see in the middle here, I gave a very classic and famous formula, which is called the Fraunhofer or radian distance. Based on this, we can calculate the boundary between the so-called near field and the far fields. And we can see the formula is given by 2 times square of d, where the d is the aperture size of the antenna array, and then divided by the lambda here, which is the signal wavelength. And if we substitute some typical attribute standards or the frequency into this formula here, we can calculate the so-called the boundary of the near field region, and we can find that if we try to use some higher frequency bands, which this level size antenna array, which is 0.5 meter, as large as our iPads, we can see the near field region can be extremely large, which can span tens or even hundreds of meters. So, which means that this is really a very critical problem when we design the MIMO system in the future. And based on these effects, many people began to research about what can we do in the near fields. And I think the most famous or the most well-known technique in the near field system is the beam focusing, which I demonstrate in this figure here. The difference between the beam focusing to the conventional beamforming is that we can see in the first figure here, This figure demonstrates the conventional far-field system, where we typically model the wavefronts of the transmitted wave as the planetary wave. So in this case, if we do the beamforming, we can only do a technique which calls beam steering. This implies that when we try to illuminate a beam towards a specific user or targets, we must illuminate the whole direction of the user. So in this case, if there are two users or targets in the same direction, we cannot identify them. There must be a very severe inter-user interference. However, if we use the near fields modeling methods, we can see where we typically use the spherical wavefront like in this figure here, we can actually achieve a more advanced beamforming technique, which is called beam focusing, which means we can focus the beam as the specific location, like in this figure here. So in this case, many people claim that we can use this kind of beamforming technique to identify the user in the same direction, but as the same as different distances. So in this case, we can serve more user in a specific space, and thus also reducing the inter-user interference. And apart from the beamforming, many researchers also focus on how to use the spherical wavefront in the near field to increase the degree of freedom of line-of-sight channel. If you have to do some research about the far-field millimeter wave system, you will find that if we use the far-field model to model a point-to-point MIMO system, the rank or the degree of freedom of the such a far-field MIMO channel will be only one, which means we can only transmit one independent data stream in such system. However, in the near-field one, thanks to the spherical wave propagation, like in this figure here, the antenna as the receiver here can be able to identify the signal transmitted by individual antenna at the transmitter. So in this case, we can transmit more data stream in the line-of-sight channel, and therefore we can achieve a higher multiplexing gain. Yeah, both these enhancements of the degree of freedom in line-of-sight channel and this beamforming technique are the most popular research topic in the near field nowadays. However, in this talk, I will more focus on less explored research topic for the near field, which is called the non-uniform Doppler frequency. If you have to do some research about the OFDM ISAC or the OTFS, you will find that when they're modeling the so-called far-field MIMO ISAC system, there's a very typical assumption that all the antenna as the antenna array will experience the very same Doppler frequency. However, this assumption will no longer be true in the near fields because as we can see in this figure here, if we try to model the Doppler frequency in the near fields, we must consider two components of the velocity. The first one is the radial velocity, and the second one is the transverse velocity, which you can also call it the angular velocity. And if we try to calculate the Doppler frequency at this antenna here, we must calculate the projection of both of these two velocities in this line-of-sight direction. So in this case, if we calculate all the Doppler frequency for all antenna, we can find different antenna will exhibit different Doppler frequency, and you can calculate it based on this formula here. So in this case, maybe it will not be good for the communication because if you try to design some delayed Doppler domain modulation, such as the OTFS, ODDM, or FDM, you must consider a more complex Doppler frequency in the MIMO system. However, in my mind, I think it's really a beautiful conclusion for the sensing technique. This is because, as we know, in the conventional far-field system, we can only capture the radial velocity of the targets, which means we can only have partial motion states. However, in the near field system, because of these kinds of non-uniform Doppler frequency, we can capture the full motion states of the moving user, which means we can have both the direction of the velocity and the amplitude of the velocity. Yeah, and so we can do some estimation technique like the maximum likelihoods. And in this figure, I show the likelihood function for the velocity estimation in the near fields. And as we can see, for the figure on the left here, where I show the likelihood function of the radial velocity, we can see there is always a main lobe around the ground truth, even if we increase the distance between the moving user and the antenna array. This is because the information of the radial velocity is always there, so we can estimate it. However, for the transverse velocity, we can see if we try to increase the distance between between the antenna array and the user, the main lobe of this likelihood function gradually disappear. So this is because as the user approaching the far fields, the information of the transverse velocity also gradually disappear. So now we know that in the near field region, we have the full motion states, which means we can estimate both the radial velocity and the transverse velocity. So we can use these kinds of information to do some system design. For example, we can use this information to track the user. If you have some research experience about the target tracking in the far field system, you will find that there is a dilemma in the far field tracking system. The reason is as following. As we can see in these two formula here, I show how we can estimate the location of the user in the next time by using the location of the user in the current time as the velocity of the user in the current time. We can see if we try to accurately estimate the location of the user in the next time, we must know these four information, which is the distance, the angular, the radial velocity, and the angular velocity, which is also the transverse velocity. However, in the far field system, we can only estimate the angular information and the radial velocity information. So, which means it is impossible to track the user's location with this very simple formula here. So the very common assumption in the current literature is that we always assume that we know that the user are following a specific track. For example, we assume the user following a straight line. So in this case, we can use some priori information to calculate the location of the user in the next time, even in the far fields. However, in the near fields, we do not need this kind of assumption because the estimation is very straightforward because we have the full velocity information. And in these two figures here, I show how we can estimate the user's location in the next time by using the Kalman filter. And you can see we can have a very accurate tracking results. Okay, this is all about the near field one, and in the next, we will talk about the ultra dense array, and I will focus on how we develop from the discrete one to the continuous one. And the first, some backgrounds about the continuous MIMO. And as we know, we always try to use a larger and larger MIMO array and also have them operating in the higher frequency bands. So in this case, we must have a denser and denser array, of course. This is because there are two reasons. The first one is that as we increase the operating frequency of the MIMO, we need to scale up the array to keep the same coverage. This is because we know that if we try to increase the frequency, we must have a higher path loss. So we must increase the number of the antenna to compensate for these kinds of increased path loss. And another reason is that with the developments of the meta material, for example, nowadays we have the meta surface or the rays. With this kinds of technique, we can really develop the an antenna array with sub-half-wave wavelength deployments. So in this case, the MIMO will gradually become more like a continuous one, like the figure on the right here. And from another perspective, I mean, from the antenna design perspective, design a continuous MIMO is also a long-standing goal in the antenna design. For example, since 1960s, there's a very well-known concepts in the antenna society, which is called the current phase antenna, which means we want to design a current phase which has a controllable and continuous currents distributed across a continuous surface. So in this case, we can have a very high degree of freedom. As in this figure, I also show very reasons example about the hardware developments of the current shapes based on these kinds of photodiodes devices. And due to the continuous nature of the continuous MIMO, most of the researcher think about modeling these kinds of systems from the electromagnetic theory perspective. For example, apart difference from the conventional MIMO, we usually model the transmit signal as the transmit continuous MIMO as a source currents. And these kinds of source currents will excite electric fields as the receiver. I mean, the continuous electric fields as the receiver continuous MIMO. And the relationship between these transmit currents and the receive electric fields can be calculated based on these kinds of Green's function approach, which is approach to have a solution for the Maxwell equations. And to be simple, I just give a formula between their relationship here. And you can see if you have a tripolarized transmit MIMO and a receive MIMO, we can have a formula like this here. Here, the tripolarized means that, as we know, for the electromagnetic fields, we have the 3 direction in the spatial domain. So the tripolarized means that the MIMO has the ability to control all these 3 dimensions of the electromagnetic fields. And it's all the same for the receiver. It can observe or receive the whole 3 dimensions of the electromagnetic fields in the spatial domain. So this kinds of MIMO is called the tripolarized MIMO. And of course, we can also have a simpler model if we assume both the transmitter and the receiver are unipolarized, which means we can only operate on or transmit information on only 1 dimension of the electromagnetic fields. So in this case, we can have a scalar version of this formula here. And when we compare these kinds of continuous MIMO system model with the discrete MIMO system model, we can see a very big difference because for the discrete one, we usually model them based on the discrete vector or matrices. However, for the continuous one, all our modeling is based on the continuous operators. So you can regard these kinds of continuous operator as a matrix or vector with infinite dimensions. So they are quite different. So based on this big difference, a very natural question is that how can we design the beamforming for such kinds of infinite dimensional matrix or vectors? And nowadays, the most straightforward method to solve these kinds of problem is based on the discretization, which means we sample this continuous MIMO at some specific location. So in this case, we can transform these kinds of continuous signal model into a conventional discrete one. So in this case, we can still use the conventional signal processing technique, such as the conventional zero forcing or the or the MMSE receiver or transmitter to solve these kinds of system model. And for the discretization, the most efficient discretization methods nowadays is to do is in the wave number domain, which is the Fourier transform of the spatial domain. However, for these kinds of discretization problem, there are two disadvantages. The first one, of course, is the inevitable discretization loss. Because we sample the continuous function, we must have some information loss. However, apart from this straightforward problem, another problem is that after the sampling, we will get extreme large matrix or vectors to process. Just give you a very simple example. For example, if you do these kinds of wave number domain discretization for example, 0.5 square meter continuous MIMO as 15 gigahertz frequency. I remember you will need more than 5,000 dimensional matrix to solve. So in this case, the computational complexity will be extremely large. So which means you cannot implement this kind of algorithm in practice. And based on these two facts, our research group began to think about, can we design the beamforming without this discretization, which means we directly solve these kinds of continuous model. And just to give an example here, I write the formula of the SINR of a MIMO, of the multi-user MISO system, which means we have a continuous transmit aperture array. And then for each communication user, we have only one receive antenna. And for these kinds of system, we can write the SINR like in this formula here. For both numerator and denominator, we can see we have the calculation of the continuous function here. And of course, this kinds of optimization problem is quite different from the conventional one. So, and if you know some knowledge about the functional analysis, you will find that this is a classic functional optimization problem. I mean, the functional here, this word here means a special function which takes the continuous function as the input and then output a scalar. And now we, based on these facts, we began to think about, can we use the calculus of variation to solve these kinds of problem? And the calculus of variation is a very classic and well-known method for the functional analysis. And the answer is also yes. We know that if we try to solve the conventional optimization beamforming problem, we usually use those kinds of KKT conditions or the Lagrangian functions, and then we calculate the derivative of this Lagrangian function, and then we can get the optimal solution. However, for these kinds of continuous one, the calculation of the derivative is not straightforward. So in this case, we need to turn to these kinds of calculus of variation to calculate the derivative of these kinds of continuous function. And the idea is given in this table here. For example, for the discrete MIMO, we have a function like this. And then our optimization problem will be scalar or vector or matrix. And then we can calculate the derivative of this function with respect to this scalar here. And then we set this derivative to 0 and solve this function. And then we get the optimal beamforming. As if we move to the continuous one, we will have a functional, which is can be expressed like this here, where this functional take the continuous function as the inputs and output a scalar. And then our optimization variable will be a continuous function. And then we can calculate the variation, which is defined in this very complex formula here. And by setting this variation to 0, we can also gets the optimal beamforming after some very complex calculation. And apart from these kinds of derivative problem, another very important problem to solve for the continuous beamforming is that we need to solve the inverse of infinite dimensional matrix, which is also the inverse of the continuous function. Actually, the inverse of the matrix is a common calculation in the beamforming if we try to do those kinds of advanced beamforming like zero forcing or MMSE. You need to calculate the inverse of a whole matrix. As the inverse of the discrete matrix is quite simple, like in this formula here, and you can just input the code into the MATLAB, and then you can easily get the results. However, for the continuous one, the definition of the inverse of matrix or the infinite dimensional matrix is totally different, and I give its dimension its definition in this formula here. And here, this function is the Dirac delta function. And to solve these kinds of problem, solving these kinds of problem is very, very difficult in general. And a common method is that we can transform these kinds of calculation into the Fourier domain. You can see these kinds of calculation is essentially a convolution. So if you transmit into the frequency domain using the Fourier transform, you can transform it into the multiplication. So in this case, you can easily to calculate its inverse. And then we need to use the inverse Fourier transform to transform it back. However, by using this general method, it's very difficult to get a closed form solution of the inverse. But fortunately, we found that for most optimization problem in the wireless communication, these kinds of function here will take like this specific form. And for these kinds of specific form, we can calculate its inverse like this formula here. So there really needs some very difficult mathematical derivation by obtaining these kinds of formula. So if you are interested in the detail, you can refer to our this paper here. And now we have solved two important problems. The first one is that we can calculate the derivative of a continuous function. And the second one is that we can calculate the inverse of the continuous function. And based on these two results, we can indeed derive the optimal structure of the beamforming for continuous MIMO, like in this table here. And in these two papers, we derive 4 important results for the continuous MIMO. The first one is the optimal structure of the continuous MIMO, and the remaining 3 results are about the MRT zero forcing and MMSE beamforming for the continuous MIMO. And if you compare these results with the conventional discrete results, you can find they have a very similar solution, which means they are consistent with each other. However, although they are very similar, obtaining these results really needs a great effort. For example, we have mentioned how we calculate the inverse and the derivative of a continuous function. And now we have this kinds of optimal structure. Of course, we can, based on this structure, to design some very efficient algorithm. And in this paper here, we indeed design a very efficient algorithm based on these kinds of calculus of variation. And we also compare its performance with the conventional Fourier-based discretization methods. And in this table here, I compare this running time or the computational complexity between these two algorithms. And you can see for the calculus of variation methods, which we aim to directly solve the continuous optimization problem, we can have almost unchanged running time for all the aperture size and the carrier frequency. However, for the Fourier-based methods, the Fourier-based discretization methods, the running time will be significantly increased if we increase both the aperture size and the carrier frequency. And of course, if we compare this weighted sum rates performance, we can see our proposed methods is also outperform the conventional discretization one. So in this case, we can have now we have a much efficient algorithm which have lower complexity and higher performance. So this is indeed what we want. And of course, apart from the very simple multi-user method system, we can also study the point-to-point MIMO system, which is more complex. And for these kinds of MIMO system, we can derive is achievable rates like in this formula here, which is also very different from the conventional one. For the conventional point-to-point MIMO system, if you try to design the beamforming, it's very easy because you just do the SVD or the end-gain decomposition of the channel, and then you can get the optimal transmitter and the optimal receiver. However, for these kinds of continuous MIMO, with this formula here, you need to do the SVD or the end-gain decomposition of this continuous operator. So, which is computationally impossible for our current computer. So in this case, we really need to directly solve these kinds of problem. And fortunately, with our previous results on the calculus of variation and the inverse of the continuous function, we can indeed also derive the optimal structure of the point-to-point MIMO in these two formulas. And these two results are from our very recent work here. And if you are interested, you can also read this paper here. And based on these kinds of optimal structure, we can, of course, also design a very efficient optimization algorithm than the conventional Fourier-based methods. And similarly, we can have a lower complexity and also a better performance. And apart from that, these kinds of non-SVD algorithm can achieve a SVD-like performance. So which means we can have independent transmission of the data stream between this transmitter and the receiver here. Okay, that's all about the continuous MIMO. And the next topic is the flexible array, and I will focus on our very recent research topic, which is called pinch antenna. And actually, flexible arrays is a very hot topic in the recent years, and there have been so many flexible arrays, and I just give 3 examples here, such as these kinds of fluid antenna, bulb antenna, and these kinds of reprogrammable surface. And for all these kinds of flexible arrays, we aim to adjust the location or even the shape of the antenna array to enhance the spatial degree freedom. However, for all kinds of these kinds of flexible arrays, there are 2 big challenges, like in this figure in the bottom here. The first challenge is that there will be a blockage issue, and the second challenge is that there will be a high free space pulse loss, even as the high frequency bands such as the millimeter wave or terahertz. And these 2 challenges are actually the inherent challenge for the wireless communication, and all origin from the broadcast nature of the wireless channel. And to solve these 2 challenges, we propose a new concept, which is called pinch antenna. And the pinch antenna facilitates developments from the conventional wireless communication to a near wireless communication. Just give you a very simple example. We know that if we the always optimal solution for the communication is that for each our cell phone, we can let our cell phone connected to an optical fiber. So in this case, we can have the optimal communication throughput. However, of course, this kinds of solution is impossible in practice because we cannot slice our cell phone to connect it to an optical fiber. So in this case, the pinching antenna is a middleway solution between the optical fiber and the wireless communication. And the key idea is like this. For the conventional base station, we let the signal directly radiated into the free space. However, in the pinching antenna system, instead of letting the signal radiated into the free space, we input the signal into dielectric waveguides. So as we know, for a waveguides, the path loss is really low than the free space propagation. So after inputting the signal into these kinds of waveguides, we need to let the signal radiated into the free space again. So in this case, we can use this pinch antenna here. The pinch antenna is a totally passive device, like our clothespin. We can pinch this kinds of antenna onto the waveguides, and then at the points of this pinch antenna, the signal will be radiated into the free space. So in this case, we can use this kinds of pinch antenna to solve both this blockage issue and the path loss issue. And to just give you some example, we can go to the next slides. In this slides, I show the NTT Docomo's test on the pinch antenna. Actually, this kind of pinch antenna concept is originally from the NTT Docomo, which is a Japanese telecom company. And in their test, they show how can we use the pinch antenna to enable the radiation of signal from a waveguides. And you can see these two figures here. In this figure, there is no pinch antenna pinched on the waveguides, so there is no signal here. And once we pinch this antenna on the waveguides, like shown in this figure here, we can have a signal radiated into the free space, and then we can have the receiver to receive the video here. So by using these kinds of technique, we can really solve the conventional blockage issue and free space have free space path loss. And apart from that, due to the passive nature of the pinching antenna, we can also very easy to change the position of the pinching antenna. So in this case, we can also have some similar feature to the conventional mobile antenna. So we can have a very high recoverability of the antenna array. And in the last slides, I show some our recent simulation results about the pinch antenna system. And in the figure on the left here, I show the communication performance, where I gave some results about how much power we need to achieve a TARDIS SNR as the communication user. And you can see the pinch antenna can achieve almost more than 10 dB reduction of the transmit power. And of course, for the localization, where we try to use the pinch antenna to localize the user in a specific region of interest. And you can also see the pinch antenna can also achieve a much lower position error bounds than the conventional MIMO system. And all these results are due to the really high reconfigurability of the pinch antenna along the waveguides, as I mentioned before. Yeah, okay. That's all about my presentation here. And I also have some open source codes in this link about our paper on continuous MIMO. If you are interested, you can check our GitHub website here. Okay, that's all. Thank you.
Thank you, Zhaolin. Very, very interesting work. Guys, we have time for a very couple of very short questions. How do you think? I have two questions. The first about the near field stuff.
Yeah.
Have you considered any issues like misplacement of the antennas or correlation or issues like that might require calibration of the antenna?
No, not in my work. Actually, I only consider a very ideal condition, such as the perfect collaboration or the perfect correlation, cancellation, something like that. Yeah.
Okay.
Yeah.
Okay. Because I guess that this would cause a problem of, the focus is not going to be so sharp as it is right now, right? So when you,
Yeah.
yeah, okay, good. So my next question is about the continuous MIMO work.
Mm-hmm.
Is it possible to, let's say, you take a gigantic MIMO problem, so you have very, very large number of discrete antennas, but then you approximate it as a continuous antenna. You solve, for example, a beamforming problem, and then you subsample the solution to extract the weights of the discrete one.
Yeah. I think it will be a mainstream solution for the practical implementation for the continuous MIMO because it's really impossible to achieve the real continuous in the practice. So, and one of the most common solution nowadays to approximate this kinds of continuous MIMO is to use ultra dense antenna array. So for design those kinds of problem, of course, you can first solve a continuous one and then extract the weights of each antenna. I think the performance loss will be quite negligible because the ultra dense array is really very close to those continuous one. Yeah.
Okay.